Hi guys, let's start today's class. In the previous class, we learned about the associative cache. So actually, when we learned about the cache memories, so we first learned the direct mapped cache, and then I also explained the disadvantage of the direct mapped cache. So what is the disadvantage? So in the direct mapped cache, the address. So a certain memory block is only can be only mapped to the uh, designated the cache line, and then the cache set of a direct mapped cache can only have one block. So which means that so actually a set can be mapped to the many memory blocks, but this cache set has only one slot for storing this memory block. So what is the problem? So direct mapped cache, even though this direct mapped cache may have many empty sets, but many memory blocks can be mapped to the only one set or so small number of sets. So which means that so if this valid block is stored in a certain set of the direct mapped cache, and then only new block is fetched to the direct mapped cache, then the old blocks to be evicted from the cache. So that is the disadvantage of direct mapped cache. So we also learned some performance of the cache, and then we can measure the performance of cache using cache miss rate or cache hit rate. So if we use the direct mapped cache, the cache miss rate is relatively high. It is because the cache blocks, so the hardware resources of cache, which is the which means the cache blocks, the cache is not efficiently used with the direct mapped cache. So the possible solution for this advantage of the direct mapped cache is to use associative cache. So what is the definition of associative cache? So with the associative cache, so we can store more blocks, multiple blocks in a target set, in a target cache set. So which means that if we use the n-way set associative cache, then we can store n blocks, the maximum n blocks in a target set. So which means that even though the multiple blocks are mapped to this set of the set associative cache, but we can store maximum n blocks in a target set. So which means that even though multiple blocks are set to this single target set, that we can store multiple blocks. So which means that all the blocks, so all the valid blocks can be kept in the set associative cache. But what is the disadvantage of NA set associative cache? With the NA set associative cache, we require n comparators. So which means that we need to compare n tags of the n blocks in the target set. So comparator is the hardware resources for comparing the tag address stored in the cache. So it's more expensive, which means that the NA set associated cache requires more hardware resources. So which means that the cost of the NA set associated cache is higher than the direct mapped cache. So we can also configure our cache with the fully associative cache. So with the fully associative cache, so it's similar to the n-way set associative cache, but the n is equal to the number of total number of blocks in a cache. So which means that the fully associative cache only have one set, but with the one set can store n blocks. So, but n is very large. Actually, the cache has only one set. So in a fully associative cache, there is no concept of set index. So which means that the memory blocks can be any line of this fully associative cache if the line is empty. Okay. So with the fully associated cache, we need to require the many comparators. So which means that the fully associative cache is the most expensive cache among the fully associative cache, set associative cache, and direct mapped cache. Okay. So also we learned how the cache memories can be accessed using this block access sequence. So then with this sequence is it's not real cache access sequences. So which means that actually we select some block address which can be mapped to the same set of the cache or cache, same set index of the direct mapped cache or a set associative cache. So with the direct mapped cache, then only one block can be. So we can calculate the target index of the cache with the modular computation. So and then if we use the direct mapped cache, then these multiple block sequences will be mapped to the same index, same set. So which means that the old blocks should be evicted from the cache. So, but if this old block is re-referenced, then the cache cannot find the old block because the block was evicted by some previous cache accesses. So that is the disadvantage of the direct mapped cache. But if we use the set associative cache, then we can store multiple blocks to the target set. Okay, so which means that all the blocks can be kept in the cache. Okay, so if we use if we increase the associativity in the cache, then we can also increase the performance of cache. But I mentioned that this performance is saturated. So which means that the performance of the cache is not linearly proportional to the associativity in cache. Okay, so the good thing is that the performance is saturated. So usually the performance of 8-way set associative cache is similar to the performance of a fully associative cache. Okay, so that's why we can use some 8-way or 16-way set associative cache for the internal caches. And then I also explain how the cache can be implemented for the set associative cache. So which means that to the target index, so this is a target set. Target set can store multiple blocks, so multiple cache lines. So which means that multiple tags and then multiple data blocks will be stored to the target set. And then when the processor accesses this set associative cache, then first we need to decide the index using the address of this memory instructions, and then we can read the tags in parallel, and then the tag part of this address can be compared with the tags on this multiple cache block. And then if the tag is matched, then this is the cache hit. Okay. So please remember that in the set associative cache, the cache has multiple blocks. So the target set can have the multiple blocks, and then we can access these multiple blocks in parallel. Okay. And then because the target set can store multiple blocks, then we can consider the replacement policy. So which means that if the all target blocks are valid, which means that the target set is occupied by target sets are occupied by all valid blocks. Then in this case, if the new block should be fetched to the cache, then we need to evict the one of these valid blocks. Okay, so replacement policy means that how replacement policy define how to select the evicted block from a target set. Okay, in the direct mapped cache, we don't need to consider about the replacement policy, because in the direct mapped cache, a target cache set can only store one block. So which means that if the new block should be stored in the cache, then we can evict the old block. So only one block in the target set. But in the set associative cache or fully associative cache, we need to select which block should be evicted from the target set. Okay, and then I explained that we frequently use the least recently used algorithm. It's called LRU. So which means that the oldest block. So least recently accessed block is evicted from the cache. Okay, so it is because the cache exploits the locality. Which locality? Temporal locality. So which means that temporal locality means that if a certain data block is accessed, and then in the near future, this block can be accessed again with a high probability. So if we consider this temporal locality, the cache data, the data in the cache, then if the cache block is recently accessed, then with a high probability, then this block can be accessed again. So least recently used algorithm, the LRU replacement policy is based on this temporal locality of our data. But implementing LRU algorithm is not easy. So especially if we use the if cache has the high set associativity. So usually in a processor, in the commodity processor, the cache use the pseudo LRU. This is very similar to the LRU, but so pseudo LRU. Okay, so some simplified LRU algorithm. Sometimes we can apply the random policy, so which means that the evicted block is selected randomly. Okay, and then let's see some performance of the multi-level cache. So usually the commodity processors have multi-level caches. So actually, when I explain about the memory hierarchy, and I also explained that cache has also hierarchy. So like the L1 cache, L2 cache, and then L3 cache. And then I also explained that the L1 cache is very small and very fast, and then actually in a processor, we have separated the L1 cache like the L1 instruction cache and then L1 data cache. And then after that, the processor has unified L2 cache. And then the multi-core architecture, there are multiple cores, and then this processor usually has large shared L3 cache. So actually the commodity processors deploy multi-level cache. So this is the cache hierarchy. Okay. Then why do you use multi-level cache? So So in order to increase the performance of the processor, right? But why do we use cache hierarchy, like the memory hierarchy? The purpose of this multi-level cache is similar to the purpose of memory hierarchy. So why do you use memory hierarchy? In the high-level memory, so high-level memory is very small, but it's very fast. The low-level memory is large, but it's slow. So you can apply the same concept to the cache hierarchy, like the L1 cache and the L2 cache and the L3 cache. So L1 actually the size of the L1 cache is smaller compared to the L2 or L3 cache. Why? We need fast cache because which means that the size of the L1 cache is very small, then we can access L1 cache very quickly. Okay, but L2 is the size of L2 is larger than the L1. Why? We want to store more data in L2. And then also the benefit is that the L2 is located inside of processor. So actually, and then the DRAM is the external memory, and then this is the CPU. And then I explained that if the memory is located out of the processor, then the latency will be very high because it's the external memory, and then so which means that we need to access this memory using the PCB lanes. And then also it's very expensive. So the pin count, the pin of this CPU chip is also very expensive. So which means that we cannot use the large, we cannot implement the large bandwidth between the main memory and CPU. But if the cache is located inside of a processor, and then cache can be implemented using SRAM. So actually the performance of a cache is higher than the performance of a DRAM. But if we also increase the size of the cache, then the access latency is also increased. So which means, as I explained, if we use the large memory, then the performance is decreased. So which means that the access latency is increased. So then why do you use the multi-level cache? So we want exploit the internal memory, so internal cache actually. But if we use the very large cache, like the very large L1 cache, then the latency, the access latency to this cache will be also increased. But we want very fast L1 cache. So L1 cache is very small, but the size of the L2 cache is larger than the L2 cache. It is because we want to store more data to decrease miss rate with the L2 cache. Okay, so with this, if we use the cache hierarchy, then we can also improve the performance. So I will show the example. So in this example, the CPU-based CPI is 1. So this is the ideal CPI. And then clock rate is the 4 gigahertz. So the frequency. And then let us assume that the miss rate for the instruction is the 2%. Miss rate per instruction, not the miss. So this means that this is the miss rate per instruction. Okay. So it's a total number of instructions, and then divided by so the total number of cache misses are divided by total number of instructions. It's a 2%. And then let us assume that the memory access time is the 100 nanosecond. So what is the miss rate? So the clock, because the clock rate is the 4 gigahertz, the clock period of this processor is 0.25 nanosecond. So which means that the miss penalty is the 400 cycles. Okay. And then what is the effective CPI? So effective CPI, this is the ideal CPI, and then we need to add the increased CPI by cache misses. So this is the increased CPI by cache misses. So effective CPI is 9. Okay. So and then which means that this is the processor, and then this processor have only L1 cache, and then this we have the L1 cache, the DRAM is connected to this processor. This is the configuration of the single level cache. But let us assume that we have L2 cache, so which means that this is the processor, and then after that this processor accesses the L1, and then this processor also the larger L2 cache, and then after that the processor can access DRAM. So with the multi-level cache configuration, the L2 cache is located between L1 and DRAM. And then let us assume that the access time for L2 cache is access time to L2 cache is 5 nanoseconds. So, and then global miss rate to the main memory. So let us assume that the global miss rate to the main memory is the 0.5%. So as you can see, the miss rate is decreased because we use L2 cache to reduce the miss rate to the main memory. Okay, so which means that the size of the L2 cache is larger than the size of L1 cache, but as you can see, the access latency is also higher. It's 5 nanoseconds. Then let's calculate some increased CPI using this multi-level cache configuration. So what is the miss penalty for this L1? So, and then we can say that when the access to the L1 is missed in the L1 cache, then we need to access the L2 cache. Okay, then the access latency, latency to L2 cache is the 5 nanosecond. Then if the access is missed in L1, then this request need to access L2. So, and then which require 5 nanosecond. Then what is the penalty? So we can calculate this 5 nanosecond with the clock cycles. That is the 20 cycles. And then, so this latency is the same. So DRAM latency is the 100 nanosecond. So, and then when the this request is missed in L2, then what is the miss penalty? It's the 400 cycles. It's the same. Then the global miss rate to the main memory. So the miss rate to this is the miss rate to the main memory globally for the entire instruction. So the miss rate is reduced to 0.5% because of L2. Then the miss rate per instruction is 2%. So this is the miss rate to L1. Okay. Then what is the increased CPI? So if this is the ideal CPI, then this is the some miss penalty that is required to access L2. Okay, but the penalty is reduced because of L2. So, and then the global miss rate to main memory is the 0.5%. So we can calculate this is the miss penalty to the DRAM. Then the effective CPI becomes 3.4. And then if we compare the previous result, then we can know that the performance is increased by 2.6 times. Okay, so that is the benefit of the add to cache. So which means and also, but we need to add the internal cache inside of a processor, and then the SRAM is more expensive than the RAM. But with this add to cache, we can improve the performance dramatically, like 2.6 times, right? So with this multi-level cache, we can invest more hardware resources to L2, but with this investment, we can increase the performance dramatically. Okay. Then how can you configure the cache? As I explained, so this is similar to the memory hierarchy. So this is called the cache hierarchy. Oops. Cache hierarchy. So this means that the cache hierarchy is composed of L1 and then larger L2 and then even larger L3 cache. So usually. So the primary cache, the L1 cache means that we focus on the fast access to L1 cache because actually when we configure the L1 cache, so we design the L1 cache to have fast heap time. Okay, so which means that the size of the L1 cache is small. Okay? We can access the L1 cache very quickly, like so less than within one clock cycle, right? So for the primary cache, we focus on the minimal heat time for the L1 cache. For the L2 cache, but the size of the L2 cache is larger because firstly, the access to the memory is filtered by L1. So with the L1 cache, actually the miss rate is also is reasonable, like the less than 10% of us, like, because of the data locality observed in applications. Then we can also the miss rate is has some reasonable level. Okay, so which means that the the memory accesses are filtered by L1, and then the L2 is accessed by missed request. Okay, the missed request in L1. So actually, because of this reason, so we use the larger L2, and then actually when we configure the L2, that the main purpose of L2 cache is to reduce miss rate. Okay, so actually for L1 we want fast L1 cache, but for the L2 we want the heat time may be important because the heat time of the L2 cache is the miss penalty of L1 cache. Okay, and then as we learned, the average memory access time AMAP is the heat time plus miss rate multiplied by miss penalty. So when we consider the average memory access time of L1, so this average memory access time is also determined by this heat time and then this penalty. So this penalty is some access latency to L2. So the access latency to L2 has also some reasonable level, but it's less important than the the hit time of L1. So we focus on the bit rate when we configure the L2. So which means that the size of the L2 cache is larger than the size of L1. Okay. Okay. So usually we configure the L1 cache size smaller than compared to the L2, and then L1 block size is smaller than L2 block size. Okay. So actually we did not learn about the out-of-order processor architecture in this course because this is the some advanced level in the computer architecture field. So on the undergraduate course, we just handle the pipeline processor. So actually this pipeline processor is called the statically scheduled pipelines. Okay, and then out-of-order processor is dynamically scheduled processor. But when we consider the out-of-order processor, the performance of the memory system, so actually it's not easy to it's not easy to explain the performance of the memory system with the out-of-order processor because the execution order of these memory instructions can be out of order. So actually, which means that even though the former instruction is missed in the cache, but the following instruction, which means that the later instructions can also access cache. Okay, so it's not easy. It's not easy to analyze the performance of the memory system with the out-of-order processor, which means that we need to simulate the performance of this processor with the architectural simulator. Okay, and then let's see some performance of memory system is the performance of the memory hierarchy with the software. So and then in this topic, so we will learn how the software design influences the performance of computer system and considering the memory hierarchy. Okay, so and then let's see the this graph. So this graph just compares the performance of two different sort algorithms. Okay, so if you see that this first graph, this black line is the radix sort. It's a very simple sorting algorithm, and then you can also find the quick sort. It's a quick sorting algorithm. Okay, so if we just compare the some performance of these different sorting algorithm, and we can compare those clock cycles per item. So this means that it's the required clock cycles for sorting a single item. Okay, so which means that the total execution cycles are divided by number of items in the sorting algorithms. Okay, so this x-axis represents the size of the sorting algorithm. So which means the number of items, and then so this y-axis is in this video graph. This y-axis represents the clock cycles per item. Okay, so as you can see, the clock cycles per item is very high for the radix sort, but if the number of item is small, okay, but the quick sort so relatively faster than the radix sort, but the slightly increased the clock cycles per item. Also, we can compare the instructions per item. The radix sort, the instruction is number is higher, but when the when the number of items increases, then this instructions per item is reduced. Okay, because this is the simple algorithm. But when the quicksort is applied, the number of instructions per item is increased. And then let's see the performance of the memory system, like a cache misses per item. So we can observe the different aspect for the different sorting algorithms, right? So if we use the radix sort, this cache misses per item is very high for the small number of cache, but it's reduced. But we can observe that the cache rate is cache miss rate increases as the number of items for sorting increases, right? So which means that the data set size is increased, then this algorithm, so which means that if number of items for sorting is increased, so which means these items cannot be the total items for sorting cannot be stored in the cache. Do you understand? Because the cache size is small, and then our application is handling the large amount of data. So when the size of data is small, like here, then we can store this small sized data in the cache, and then which means that we can the performance of this application benefits from cache hierarchy, so cache memories, because this small amount of data can be stored in the cache, and then the processor can access cache memories many times. But as the data size is increased, then this large amount of data cannot be stored in the cache. So which means that when this data is accessed, sometimes firstly this part of the part of data can be stored in the cache, but when the application runs, then application will require more data. So which means that the cached data should be evicted from the cache, right? And then if the more data is evicted, and then this data will be also re-referenced by applications. So which means when the data size is increased, the miss rate can be also increased. So if we see the result of the radix sort, the miss rate is reduced. So which means that until this point, this application, the performance of this application benefits from the cache. But the data cannot be stored, the entire data cannot be stored in the cache, and then more data is evicted from the cache, and then this data is re-referenced again and again. So cache miss rate is increased. So if we just focus on the quick sort, so you can find that the cache misses per item is also low for the quick sort. But when the data size is increased, this miss rate is also increased. So what can we learn from this observation? So what we can learn is based on some data size, and then based on the algorithm used in the certain application, the performance of cache can be changed, can vary, right? Also, some application with some size, for a certain size of the data set, the performance can be dramatically increased by cache hierarchy. But the application handles the very large amount of data, then the performance can be degraded because this entire data cannot be stored in the cache. So we will see another example like the matrix multiplication. So I believe everyone knows about the matrix multiplication. Okay, so this is some example code of the matrix multiplication. Okay, and then so with the matrix multiplication, then let's see how. So in order to calculate this element, then we need to perform that multiplication for vector, the row vector of matrix A, and then the column vector of matrix J, right? So in this example, we just calculate the Cij. So which means that we with this code, so it's a matrix multiplication code, right? So for this code, we firstly calculate this element for C, matrix C, and then 2, 3, like this. And then in order to calculate this element 1, then we require the data. So the first row from the matrix A, and then the first column in matrix B. Then in order to calculate the second element of this matrix C, then we require the first row also, okay? But for matrix B, we require the second column vector, right? And then what's the problem? And then for 3, then this is reused. So this A is reused, but we require to use the column number 2, that's the third column in matrix B. So what's the problem? So if we see how the matrix multiplication is computed using this simple code, then this row vector of matrix A is reused. So which means that these 6 elements of matrix A are reused. So if the data is reused, then we can exploit cache, right? But how about the matrix B? And then in order to calculate each element of this matrix C, then column vectors are used for computation. But while this row vector is reused for this first row for calculating the first row of the matrix C, but columns are sequentially selected. Do you understand? Do you follow me? The problem is that if the matrix size is very large, so the cache size is small, and so A is this row vector of matrix A is not a problem. So the A is reused again and again in the cache. But if the cache size is small and the matrix size is large, then when this column is referenced, then this column is stored in the cache, right? And then when this column is referenced, and then this column data is stored in the cache. Then when this column is referenced, and then this column data will be stored in the cache. And then if the cache size is small, when this column is referenced, cache does not have enough space, then the previously referenced column data can be evicted from the cache because cache does not have enough space. Okay, so what's the problem? We know that, so actually this matrix multiplication will exhibit very high data locality, right? Because, so you know that for this element, okay, so for the next row of this matrix C, when you compute the elements in the second row of the matrix C, then this row of the matrix A is used, and then this column will be re-referenced. Then what's the problem? Because the cache size is small, and then because these columns are referenced, this column can be evicted from the cache. And then if this column is evicted from the cache, then we cannot find the requested data in the cache, which means that we cannot exploit the cache memory because the data is not found in the cache. So globally, we can know that this column will be re-referenced again and again. But because of the small size cache, this column is evicted. So this column is not found in the cache. And then, so this is the miss event. And then, or if access missed in the cache, then the performance can be degraded. Okay, so which means if the dataset size is increased for the matrix multiplication, then entire matrix data cannot be stored in the cache. So which means that because of the reference to this large data, the old column data can be evicted from the cache. So in this case, we cannot efficiently exploit the cache. Okay, so that is the influences from the dummy matrix multiplication algorithm. So which means that if we do not consider about the cache size for when we design our application, then this application may exhibit very low performance because of limited size of cache. Okay, so especially if our application handles large amount of data, then we need to design fancy algorithm. Okay, so they can exploit these cache memories. Okay, then how can we improve this matrix multiplication algorithm? So what is the problem? The problem of the issues in this matrix multiplication is that this dummy simple matrix multiplication algorithm, and there's the very large matrices, and then this large matrices, the elements in these large matrices cannot be entirely stored in the cache. Then, if we handle smaller matrices, so which means that if we split this large matrix into smaller sub matrices, then we can use cache more efficiently. Okay, so this is the improved matrix multiplication algorithm. And as I mentioned, with this improved matrix multiplication algorithm, then this large matrix is split into smaller sub-matrices, and then these smaller sub-matrices are used for computing the element of the result matrix C. Okay, so what's the benefit? So this C is split into smaller sub-matrices, and then in order to calculate this one, then we can use this one and this one. So which means that these small sub-matrices of matrix B can be entirely stored in the cache. And then when we compute this one, then we also use this row, and then we can also use this column. But because the size of the sub matrices is small, then we can find this data, this column vector data in the cache. Okay, understand? So this graph shows the performance of unoptimized version of matrix multiplication, and then the blocked matrix multiplication version. And then, as you can see, this y-axis represents the gigaflops, so it's the number of floating operations per second. So, and then we can compare the performance with the various sizes of matrices. Okay, there's a 32 by 32, and then 160 by 160, and then blah, blah, blah. So, and then if we apply the matrix multiplication using the unoptimized version of algorithm, then as you can see, the performance is degraded as the matrix's size is increased, right? So it's dramatically decreased. But if we use the blocked matrix multiplication algorithm, then the performance is, so actually performance is the same for the 32 by 32 algorithm. The performance is degraded slightly, but if we just compare the performance of 960 by 960 matrix multiplication, then the performance is about 2 times higher than the unoptimized version. It is because the blocked matrix multiplication algorithm can exploit the cache more efficiently. So which means that the elements of smaller submatrices can be found in the cache. So we can access these elements very quickly. Okay. So what is the lesson we learned in this example? So sometimes we require better algorithm that can exploit the cache memories more efficiently. Okay, so especially I mentioned the data size. If the data set size is very large, so like data set size is very large, this entire data cannot be stored in the small sized cache. But why do we use cache? We want to use cache to access data very quickly. So which means that we need to increase the hit rate in this cache, the small cache, right? But if the large amount of data is handled by software, and then if we just handle this data without any optimization, then we cannot efficiently use this cache. Okay, so data is stored. When the data is firstly referenced, then this data is fetched to the cache, but when the other data is referenced again and again, this old data is evicted from the cache. Okay, then when this data is re-referenced by application, then this data cannot be found in the cache. So which means that we cannot use cache efficiently. Okay, so in order to use cache more efficiently, then we need to develop the more optimized algorithm that can use the cache more efficiently. Okay, so that's why the software algorithm, software optimization is also very critical for the performance of computer systems, especially when you consider some memory hierarchy or memory systems in our processor. Then we need to design more efficient algorithm and then more optimized algorithm that can exploit the caches more efficiently, right? It's very critical actually. Actually for big data applications, which means the big data applications have a very large amount of data. So which means that the cache performance, the cache efficiency can be degraded when we run big data applications. Okay, so we can apply the more efficient cache for handling the big data application, or we can develop the more optimized algorithm that handles the big data applications. Okay, so we learned how the algorithm or big data set size influences the performance of a cache. Also, the performance of a cache is also very critical for the performance of entire systems. So we need to develop the very fancy algorithm. Okay, so now, so actually the next topic is the virtual memory, and then people moving on virtual memory, then I will briefly summarize this cache hierarchy. Okay. So firstly, we this actually you can find this slide deck. So it's a summary of a memory hierarchy. So in this slide, then this memory hierarchy is summarized. So what we learned in this memory hierarchy is summarized in this slide. Okay. So firstly, we can consider the block placement. So which means that we can consider the direct map cache or set associative cache, and then fully associative cache. Then actually we can say that this direct map cache and then NOA and the fully associative cache can be represented as the N-way set associative cache. Okay. So this N means the number of blocks in a set. Okay. So direct map means that this is the one-way set associative cache. So and then which means that in a target set we can just store one block, so one choice for replacement. And then if we use the n-way set associative cache, then which means that we can store n blocks for a single set. Okay. And then if we use the fully associative cache, so this fully associative cache has only one set. So which means that if a cache has total m blocks, then this fully associative cache is equivalent to the m-way set associative cache. So which means that the memory request, the memory blocks can be mapped to the any location of fully associative cache. Okay. Then higher associativity reduces miss rate, right? So but I explained that this is the associativity of a cache and this is the miss rate, but the miss rate is not linearly proportional. The miss rate can be saturated. Okay, so which means that the fully associative cache is the most expensive cache, but we don't need to use this fully associative cache because the miss rate is saturated by associativity. Okay, so For the direct method cache, we can compare only one tag. So which means that the set index is determined, we can access the target set of the cache. Then we can read the one tag for the direct method cache because only one block is stored for the target set of the direct method cache. Okay, so we require one tag comparison. And if we use the n ways of associative cache, then we require n tag comparison. The fully associative cache, and then we need to search all entries of this fully associative cache. But if we use the lookup table, so I will explain. So this lookup table is very similar to the page table of the virtual memory, and I will explain later. Then they firstly access the lookup table and then find the location of the data, target data in the fully associative cache. Then we can access the target block of this fully associative cache. Okay, but fully associative cache is the most expensive cache. Okay, and then when the NA set associative cache are applied, including the fully associative cache, then we need to consider the replacement policy. And we frequently use the LRU because, and we consider the temporal locality of the observed in application, then LRU is the reasonable choice for replacement algorithm. But we can apply the random algorithm. And then write policy, we learned about the write through, write back policies. Then write through means that when the write transaction hit in the cache, and then the cache block is updated, and then at the same time, this update is reflected to main memory. So this is the write through policy, but I explained that when the write through policy is applied, then the store instruction requires more cycles because this update should be reflected to the main memory, but main memory is very slow. Okay, so we do not implement the write through policy like this, so we can apply the write buffer. Okay, then what is the write back? When the write transaction is hit in the cache, then the target block, the part of target block is updated, and then we mark dirty for this updated block, and then this block is evicted from the cache, then these updates are reflected to main memory. This is the write back policy. And then I explained that the most of commodity processor employs write back policy for cache. Okay, this is the somewhat new topic, the source of misses. So which means that we can classify misses, cache misses based on the reasons of misses. So which means that why miss occurs in the cache. And then this is called the 3Cs of cache. It is because these sources of cache misses start with C, C, C. That's the same. So this is called the 3Cs of cache. The first source of miss is the compulsory misses, or this is called also cold misses. Then what is the cold misses? Cold miss means that so initially the cache is empty, or when the data is firstly referenced by processor, then we cannot find this data in the cache, right? So for example, so load A, but this A is firstly requested by this load instruction. So in this case, we cannot find this data A in the cache, right? It's obvious, right? So then this type of miss is called compulsory misses or cold miss. Okay, so when the block is firstly accessed, the firstly requested, then this is obviously miss, and this miss is called the compulsory miss. And then another source of miss is the capacity misses. So as I mentioned, the cache size is smaller than the main memory size. So, and the cache has the limited size. So, which means that the miss rate, even though the block is, because of the limited capacity, even though the block is firstly referenced, this block can be evicted from the cache. And then after that, this block can be re-referenced by processor. Right? But this block is already evicted from the cache. So if the cache size is small, then this rate can be increased. So if we use the larger cache, then we can reduce the miss rate. So which means that this kind of miss can be caused by limited size of cache, right? And then this kind of misses are called capacity miss. Okay. And then another source of misses is the conflict misses. Okay, conflict misses. So this kind of miss means that if we use for example, if we use the fully associative cache, then we can store the referenced block in any location of the cache. But if we use the set associative cache and then or direct mapped cache, then we can observe that the miss rate is increased because of limited associativity in cache, right? So complete misses means that because of limited associativity in cache, the cache misses can be increased. Okay. So this kind of misses are called the complete misses. So we can classify the misses in cache with compulsory misses, and then capacity misses, and then conflict misses. So, and then if we analyze these misses, then we can analyze why the cache misses are increased by which factors. Okay, like cold misses, capacity misses, or conflict misses. And so this table summarize the cache design trade-off. So which means that we can configure cache like this. We can also configure cache size. We can configure associativity in cache. Also, we can configure the block size in cache. So which means that we can set the different configurations in cache. Then we can expect some impacts, some influences from these different configurations. Okay, based on these three C's of cache. So let us assume that if the cache size is increased, so which means that we can apply the larger cache, then we can reduce the capacity misses. Right? We cannot avoid cold misses, even though we use the very large cache, because firstly the data is not found. Data does not exist in the cache. Firstly, because and then in this case we cannot avoid cold misses with a larger cache, but we can reduce capacity misses. Okay, And so this is the advantage of large cache. But what is the disadvantage? If the size is increased, then the access latency can be also increased. So which means that the hit time is increased. So if we consider the AMAT, so it's the hit time plus miss rate multiplied by miss penalty. Hit time is also critical for the performance of a cache. So may increase the access time. This is the negative performance effect. So also we can increase the associativity in cache. So which means if we increase the associativity, then we can decrease conflict misses, because we already learned that if the set associativity is increased, then the miss rate is reduced. So which means we can reduce the conflict misses. But we also the cost is increased or negative impact effect. The cost can be increased, also the access latency can be increased. And the block size. If we increase the block size, then we can reduce cold misses, right? Understand? So think like this. So we are accessing A0, A1, A2, blah, blah, blah. So, and then let us assume that the size of each element is the 4 byte. So if we use the 8 byte block for cache, then when the first A0 is referenced, then we fill A0 and A1 in the cache because the block size is 8 byte. So this is the cold miss, but because the block size is larger than the size of an element, then the next reference is the hit in the cache, right? So we can assume that if this array has the infinite element, then the cold miss rate is around 50% if we use the 8 byte of block. But if we increase the block size as the 16 byte, then for the first reference, then we store 0, 1, 2, 3 in the cache. So in this case, the miss rate is reduced to 25%. So firstly, the first reference is miss, but for the A1, A2, and A3 is hit in the cache, right? So if we increase the block size, then we can decrease compulsory misses, like cold misses. But problem, the miss penalty can be increased because we need to fill the larger block, and then also another miss rate can be increased because of cache pollution. So which means that if the cache size is limited, so which means that if we just assume the same cache size, then if we increase the block size, then the number of blocks in this cache is decreased. Okay, so which means the cache cannot. So even though the small number of the only part of this block is used, but this cache need to store entire block. So which means that the cache can be inefficiently occupied by unused data, and this is called the cache pollution. So the miss rate can be also increased because the cache includes the small number of blocks, and then cache is also influenced by cache pollutions. Okay, so cache configurations also influences the cache performance. Then we need to consider some optimal cache configuration. So by taking the cache can gain some higher performance. Okay, but we need to consider some different configuration factors, and then we need to set the cache using some optimal configuration based on the analysis on our workload. Okay, so yeah, I also covered the 3 C's of the cache, like a source over misses. This is somewhat important topic in the cache, and then so in the next class, we will cover the virtual memory. Okay, so it's another important topic in the memory hierarchy. Okay, so I will stop here, and if you have any questions, then please post your questions on Piazza. Okay, so thank you guys, and then see you in the next video lecture, the recorded lecture. Okay, bye guys.